Imagine a self-driving car navigating a bustling highway. It must make split-second decisions: when to change lanes, how to avoid collisions, and how to react if another driver suddenly brakes. But how do we teach a machine to handle these high-stakes, real-world scenarios safely and efficiently? That's the challenge researchers are tackling with a groundbreaking approach called scenario-based hierarchical reinforcement learning, or SAD-RL. Let's break it down. Traditional AI methods for autonomous vehicles often struggle with two critical issues: learning efficiency and adaptability to novel situations. Think of it like learning to drive by trial and error in a world where every road is different. You might crash a lot before figuring things out. Bad news for safety and speed. Enter SAD-RL. This framework merges two powerful concepts: hierarchical reinforcement learning, HRL, and scenario-based training. HRL works like a team. High-level decisions, like merge into the left lane, are separated from low-level actions like steering and braking. It's like having a navigator and a driver working in tandem. Meanwhile, scenario-based training lets researchers design specific, challenging situations. Think of them as training wheels for the AI, exposing it to tricky scenarios like sudden lane changes or emergency stops. Here's how SAD-RL works. The AI first selects a maneuver template, a high-level plan like prepare to overtake. Then a low-level controller executes the move, handling the nuts and bolts of acceleration, braking, and steering. But the real innovation lies in the scenario environment. Researchers create both synthetic, computer-generated, and real-world scenarios, like a car cutting in front at high speed or a pedestrian suddenly crossing the road. These scenarios are carefully designed to push the AI to its limits, ensuring it learns from the most critical situations. Why does this matter? Let's look at the results. In tests, the SAD-RL system outperformed previous methods. It handled both simple tasks, like staying in a lane, and complex challenges, like avoiding a collision in a crowded intersection, all while learning faster. Ablation studies, which mean testing what happens if you remove parts of the system, showed that both the hierarchical structure and diverse scenarios were essential. Without them, the AI struggled. But how does this translate to real life? Imagine a self-driving car that's not just following rules, but understanding the road. It doesn't just react to what's in front of it, it anticipates risks, like a car swerving into its lane or a pedestrian darting across. This is the future of autonomous driving: systems that learn from structured challenges and real-world unpredictability, adapting dynamically to ensure safety and efficiency. Now, let's dive deeper into the technical details. SAD-RL's hierarchical structure is key. The high-level policy operates in a scenario-specific space, choosing actions like brake or change lane based on the environment. The low-level policy then translates these decisions into motor commands, such as throttle and steering angles. This separation allows the AI to generalize across tasks, while maintaining precision in execution. But the real magic is the scenario-based training. Researchers use a mix of synthetic data, like simulated highways, urban streets, and edge cases, and real-world data, from actual driving logs, to create a diverse training environment. For example, a synthetic scenario might simulate a pedestrian crossing at night, while real-world data could include a sudden obstacle on a rainy day. By combining these, the AI isn't just memorizing patterns, it's learning to reason about risks and trade-offs. Let's talk about the experiments. The team tested 4 algorithms: DQN, QRDQN, PPO, and A to C. Only A to C showed consistent learning. When trained on a simple scenario, like a car suddenly braking, A to C improved over time, reducing collisions and increasing successful drives. The others either failed completely or couldn't adapt. The breakthrough came when they tested A to C on diverse scenarios. They created policies like PI-A, trained only on Type A roads, PI-FUL, trained on all types, and PIOS plus High D, a mix of easy synthetic and real-world data. The results: the hybrid PIOS plus High D outperformed all others, achieving over 69% success across all test cases. Why? Because it learned from both structured challenges and real-world unpredictability. But SAD-RL isn't just about driving. Its principles apply to any complex, safety-critical system, like robotic surgery or industrial automation. The key takeaway: hierarchical structures and scenario diversity are non-negotiable for robust AI. Without them, systems can't adapt to the real world. So what's next? Researchers are already exploring ways to scale SAD-RL to more complex environments, like multi-agent scenarios where cars must coordinate. Tools like Common Road Benchmarks and Stable Baselines 3 are making this possible, but the core idea remains the same: teach machines to think like humans, not just follow rules. The future of AI isn't just about faster processors or better sensors. It's about building systems that learn, adapt, and understand. And with frameworks like SAD-RL, we're one step closer to that reality. Thanks for watching. If you want to dive deeper into the research, check the links in the description. And don't forget to like, subscribe, and hit that bell for more insights into the cutting edge of AI. Until next time, stay curious.